Hi there, and welcome to the Maple Mission Overview, short for Mars Atmospheric Probes Leading Exploration. This mission was developed for the 2024-2025 AIAA Undergraduate Spacecraft Design Competition by Georgia Tech's AE 4332 Group 6. Our objective? To support future human exploration of Mars by delivering critical science data, detailed topography, atmospheric profiles during descent, and surface radiation levels. Maple's hybrid approach uses both an orbiter and descent probes to maximize scientific return while maintaining high reliability throughout flight-proven hardware. This mission was conducted by 7 undergraduate aerospace engineering students at the Georgia Institute of Technology. Here you can see our mission statement and overview. Maple seeks to perform atmospheric analysis, surface mapping, and radiation detection on the Martian surface to support future manned mission through the validation of potential landing sites for human exploration, as well as providing high-fidelity re-entry data to aid in future mission planning. Maple launches aboard a SpaceX Falcon Heavy from Cape Canaveral in December of 2028. After reaching low Earth orbit, it performs a Hohmann transfer to Mars, arriving after a 10-month cruise. Upon entry to the Martian sphere of influence, it uses an aero capture maneuver to slow down and enter an elliptical orbit. Then, over a 3.5-month aero braking campaign, Maple reduces its apiaxis and enters a 380-kilometer circular sun-circumference orbit. From orbit, Maple maps at least 60% of the Martian surface to help identify 2 promising landing sites. The orbiter then deploys 2 atmospheric probes to descend into those regions, collecting high-resolution entry and surface data. The table below outlines the mission level and science objective requirements that guided the design of our Maple mission. These requirements were directly derived from the AIAA competition request for proposal, the RFP, and aligned with NASA's Mars Exploration Program Analysis Group, known as MEPAG's scientific goals. Completion of these requirements will ensure a successful mission. What's shown here is a science traceability matrix outlining each of our science objective requirements and how they are divided throughout the orbiter and the deployable. Let's now walk through Maple's concept of operations across its key phases. The mission begins with a launch aboard Falcon Heavy. After stage separation, Maple is injected into circular low-Earth parking orbit, awaiting the proper alignment for Mars transfer. On December 5, 2028, Maple performs a 3.5 km second burn to initiate a Hohmann transfer. It cruises for approximately 308 days, performing trajectory corrections and health checks. At Mars arrival, Maple performs a preparatory pointing maneuver and enters the atmosphere at 150-kilometer altitude. Atmospheric drag slows the spacecraft, saving about 803 meters per second in delta V. Maple is now captured in a highly elliptical Martian orbit. Over the next 108 days, Maple executes 355 aerobraking passes to circularize its orbit. A periapsis altitude controller and a bank angle controller ensure thermal loads and orbital parameters retain within limits. Probe descent is controlled with a parachute and retro-rocket sequence. The probes begin radiation monitoring using their radar instrument, collecting daily fluctuations of galactic cosmic rays and solar particles. Data is transmitted via UHF to an orbiter and relayed to Earth. The orbiter continues mapping Mars for the remainder of its 10-year mission, maintaining its sun-synchronous orbit via station-keeping maneuvers, while the probes collect seasonal radiation data to support site selection for future human missions. Our instruments align with NASA's MEPAG objectives and the AIAA competition RFP. Marley, our Mars LiDAR instrument, maps terrain and measures global wind patterns with sub-meter resolution. SpyCam complements this by collecting ultraviolet and infrared atmospheric spectra via limb grazing and occultation. FADS measure pressure and temperature throughout hypersonic and parachute descent. COMARS Plus monitors thermal loads on the probe surface during entry, and RAD tracks surface radiation, including galactic cosmic rays and solar energetic particles, to assess long-term habitability. All instruments are heritage systems with high TRL, giving us confidence in performance and reliability for our mission. The pictured CAD model outlines how each of the subsystems are placed throughout the orbiter. The CAD model also highlights probe instrumentation and how they are placed in accordance to each of our subsystems. The table below details how each of the subsystems work together to achieve mission objective and science requirements. Maple's success hinges on seamless coordination between all subsystems. Every component is designed not to just work in isolation, but in harmony with the rest of the vehicle architecture. Over a typical week, Maple completes 105 sun-synchronous orbits. In each 95-minute orbit, subsystems coordinate tightly. For example, power from solar arrays not only drive science instruments, but also support thermal control systems, especially during eclipse periods. The attitude control and determination system provides ultra-stable pointing for Marley and SpyCam, while also maintaining orientation during data relay, aerobraking, and probe deployment. The following budgets serve to prove that Maple's mission is not only feasible, but realistic in terms of current technology and developing future exploration. Maple's budget is at $987 million, staying below the $1 billion gap. Monte Carlo simulations show an 87% chance of staying within budget. The table to the left details identified technical and operational risk. Based on the mitigation strategies in the table, the mission has a moderate to high feasibility of success. All identified risks fall within NASA's green or yellow matrix zones, indicating a low to moderate concern with effective countermeasures in place. To work towards our mission's success and meet performance requirements, the next steps of Maple's development include addressing the following challenges. These steps will solidify Maple's technical readiness for detailed design and future development. To conclude, Maple represents an innovative yet realistic path to supporting human exploration of Mars, leveraging flight heritage, strong subsystem integration, and scalable science objectives. With a clear focus on mission feasibility, Maple stands out, ready to deliver high-value data that will shape the future of planetary exploration to Mars and beyond. Thank you for watching.